Okay, here we go, functions and function notation. So here's a function, its name is sine, we abbreviate it as Sine. This is the name of the input, we like to call that x. Over here is a representation of the function. But hey, look at this. This is different than that, isn't it? Yes, it is. It's a different collection of pin strokes, but it's the same function. Is it? It's a different representation of the same function. How are these both have the same name? Well, if I plug a number in here and the same number over here, well, the outputs are going to be the same value. No matter what you plug in, you're going to get the same thing out, no matter which representation you use. So, what is the function? This is the name of the function. This is a representation of the function. Here's a different representation of the function. Oh, but wait, look. I don't have to call my input that. I could call it this. What's the difference? They're both collections of pin strokes. They're just a symbol that represent the input. But what is this? That doesn't look anything like that. Well, we like to think of that symbol and interpret it as an angle and a right triangle. And if we do that, interpret this number as being the measure of an angle, to figure out the output of the function, we could imagine this right triangle and look at the ratio of the side opposite to the angle and the hypotenuse and look at that ratio. That ratio is the same value as if you took, instead of plugging the number in here, plugged it in there. It's the same thing that would have come out of this guy. Looks completely different interpretation, different symbols, the same idea. Now what about this? Well, this is just another way of writing opposite and hypotenuse. I could call it the radius and the y value. Why would that be a y value? Well, if you put this right triangle in a circle centered where this point is right at the origin, well, now this thing has an x and a y. Cool. Well, since this ratio of y to r is true, well, it's the same value no matter how big of a circle you draw. Let's pick the easiest circle. Nobody likes fractions, so let's pick a circle where r is 1. If you do that, then if you want to know what sine of a particular number is, we can think of it as, instead of this, an infinite number of things to add up, we can think of it as being an angle, and we can look at our circle of radius 1, and if we happen to know this coordinate that corresponds to that angle, then boom, I know the sine of that number. So for instance, if I have sine of pi over 2, well, instead of putting pi over 2 here and here and here and here and here and trying to add up an infinite number of numbers, I can think of this as an angle in radians. Now, pi over 2 is just a number, but if I want to think of it as being in the measure of an angle in radians, which are dimensionless units, this is the same thing as 90 degrees. So if I think of 90 degrees, if 0's that way, 90's that way, here's my circle of radius 1. The y value here is 1, because again, it's a circle of radius 1. That coordinate is 0, 1 right there. This is 90 degrees. So what is the y value? 1. So instead of adding an infinite number of numbers up, think of that as an angle, look for your y value, and boom, there it is. And you might be like, hey, but that's not even a triangle. What is that? Here is a triangle. Well, once I make it to 90 degrees, it's no longer a triangle, is it? But every single other angle is a triangle. That angle gives me a triangle. This angle gives me a triangle. So yeah, the multiples of 90, you might not have a triangle, but the rule generalizes. Just look at the y value. Now you might not like radians. What were radians? Well, here's an angle. Here's a bigger angle. We need a way of measuring angles, and degrees suck. So what we did was we just drew a circle around our angle. Now this is called an arc length. We like to use the letter S. That is our angle. This is the radius of our circle. And so the way we measure an angle is simply the ratio of this to this, because that ratio is the same no matter how big of a circle you draw. If we drew the circle out here, fine. The ratio of this to this is the same as the ratio of this to this. Okay, so the measure of your angle in radians will define to be the ratio of arc length to radius. If you have length over length, the lengths cancel out, right? 2 centimeters over 3 centimeters, centimeter over centimeter, it's just a number. It's called a dimensionless unit. You've seen it before, we just didn't mention it. Back in algebra, wow. Check this out. Here's a line. What does a line have? What property? Well, it's floating in space. If I wanted to say, well, let's make myself the center of the universe, here I am on a, then yeah, sure, it has an x and a y intercept, but there's no center to the universe. What does it have? It has slope. From left to right, it's either going up or line is going down. Well, this line is going up, but you know what? This line is going up faster. So this idea of slope is something we can measure. And the way we measured it, remember that? We used the letter M and we said rise over run. Yeah? This is an actual unit of measure. Pick any 2 points. It doesn't matter which two. To get from one point to the other, I can go up, and then to the right. So rise over run. This ratio is a ratio of a length to a length. Sorry, a length to a, no, that was right. This length compared to this length. So if I went up 3 centimeters and to the right 2 centimeters, the lengths canceled out. So slope, like radians for an angle, is measured in a dimensionless unit of measure. So don't let radians like blow your mind. So there we go. We're getting closer to trig. Okay. I want you to understand the notation. So yeah, you got the right triangle approach. Here's an angle. There's 3 sides. The adjacent side, the opposite side, and the hypotenuse. Yay. If you want to put it on an XY coordinate system, groovy. Draw a circle around it. Now we could call this the radius instead. Opposite. This is our y value. This is the x value. So now we can use x's and y's in our coordinate system, which connects geometry and algebra. And great. So instead of sine of the angle being opposite over hypotenuse, right? We could say, well, it's y over r. Great, that's great and dandy, but you know what? We don't have to think of our angle as our input as being an angle. We like to call it x. Well, don't confuse it with this unit circle interpretation, right? Or the circle interpretation, okay? If you do that, we're still thinking of it as being an angle if we want to evaluate it in our head. But what if I want to graph the function? So yes, this circle, or if you choose to use the unit circle, where sine is simply the y value and you have an angle, this is a totally different universe than if you graph. Here is x and y. Here's our function. I'm going to name the input x, and I'm going to name the output y. Well, in this case, the y on the unit circle for an input called theta The y here is the same value as the y here. But if I call the input over here an angle, but over here I'm just calling it a number, and I want to actually graph this function, the graph looks like this. Doodle 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 doo, doodle doodle doo. Because when we normally graph a function, you plug in real numbers and negative real numbers. You look at the outputs and you plot the points. Whereas over here, we're thinking of the input as an angle. And well, the angle goes round and round and round and round. So every time you go around the circle, you repeat yourself. Well, radians, you go 2 pi, and then what happens? With the second time around, all the y values repeat. Then all the y values repeat. So right about here is 2 pi. So your graph does this. Boop. And then what happens? It does the same thing and the same thing. You get all the same y values, all the same outputs. So yeah, we have an xy coordinate system and an xy coordinate system. They're two different xy coordinate systems. They're both visualizations. They're a completely different universe. We can use this, the unit circle, to find the outputs for given inputs. And you can use those inputs and outputs and plot them over here to produce a graph. Yay. All right, see you in class, y'all.